We will have the first the final project presentation by Team 3, Mr. Jun Xiaowei and Mr. Akaga. Okay, they will talk about spectral and graph clustering with data analysis.
Hello, good afternoon, everyone. And I will talk about the spectral graph clustering with data analysis. And first, we are going to introduce the abstract of our project. In recent years, the spectral clustering has become one of the most popular modern clustering algorithm because for real data, we can easily translate to, by this clustering, we can easily translate to the linear algebra system. So we just to solve linear algebra problems, we have to find the eigenvalue of the matrix, and it's very outperformed by the standard by the traditional clustering algorithms such as k-means algorithm, which I introduced before. And but first look. Maybe spectral clustering looks a little bit difficult, but when we go inside, it's very easy. We have to find the actually k-smallest eigenvalues of some matrix. So in this project, we want to give an introduction about the spectral clustering, and we want to. In order to introduce that, we have to give some concepts of the graph matrix and their basic properties. And we will finally give the most common spectral clustering algorithm and how is disadvantage and advantages. And here is the introduction part. First of all, we will. We want to consider the data as a matrix with some rules we follow to translate the data and the relations into a graph. And for a graph, we can decide how the matrix we can use. Actually, the spectral clustering is works well even for larger data set. So, and also it's very, once we get the similarity graphs, we can easily to solve the linear problems of set matrix. And using the algorithm and for several times with different iterations, we can get some better results for it. So, but it's not trivial to choose a good similarity graphs. Like means for given data, how you give the rules to transfer to the matrix. This is also difficult to find out the matrix, because different way you choose the matrix, the finally coming the result will be quite different. Also. So here we want to show how the clustering link to the spectral of the matrix. And finally, we want to compare the results of the spectral clustering by using different matrix and how is better results compared to other clustering method. Now we are going to some basic concept of the graph theory. First, for given data, we can obtain one matrix we call the symmetric similarity matrix between points, where the entries A, I, G denotes the similarity between point xi and xg. So easily we can say Aig is equal to Agi. So it will be always real symmetric matrix. And for already we in the before class already we know the symmetric matrices always have real eigenvalues. That's why when we deal with the eigenvalues, it's more easier. So it's always real numbers comes. And Fox here always also is non-negative matrix. So first we are considered the weighted adjacency matrix. Already we know adjacency matrix is like if giving a graph, if the edges xi and xj is adjacency, then the Arg will be equal to 0. But the weighted adjacency matrix, that means the edge weight with different weight, with different values. So here already we mentioned here, if all elements are 0 or 1, then it is a regular adjacency matrix. That means adjacency matrix, what we are learned on the graph concept. And also same kind of definition like degree. Di is the degree of the vertex vi. That means summation of all the weight of the edges. And also here's a degree matrix with diagonal elements are the degrees. Now we are going to introduce a normalized adjacency matrix, which is simply defined by this way. And you can say that each of rows sums to 1. Then always we have 1 is the eigenvalue of the M. And 1 is the largest eigenvalue of the M. And easily we can find the corresponding eigenvector is this one from this matrix. So at least one eigenvalue always fixed for this kind of matrix. And this is a Laplacian matrix, which is denoted by L equal to delta minus A, where delta is a degree matrix. And also, this matrix also very interesting, means symmetric and a positive semi-definite matrix. That means all our eigenvalues are real and non-negative. And since each row of the Laplacian matrix sums to 0, so we have 0 is the eigenvalue, which is the smallest eigenvalue of the L. And the corresponding eigenvector, always this one. So, but if graph is disconnected, so the number of the eigenvalue equal to 0 is the number of connected components in the graph. Like if there's a graph with 2 parts, then whole graph have 2 eigenvalues equal to 0. So so this matrix gives more information, like the number of zeros will be we can see the graph is connected or disconnected. And here's another kind of matrix, which is normalized symmetric Laplacian matrix, like this way. So this is symmetric, and similar as Laplacian, they are symmetric and positive semi-definite matrix, and also smallest eigenvalue equal to 0 with eigenvector this one.
You have heard about the adjacency matrix. You also introduced the definition of Laplacian matrix. Now it's defining the normalized symmetric Laplacian matrix. Why that matrix is particular?
Oh, okay. Now I will continue for the following concept. Here's already we introduced normalized symmetric Laplacian matrix, and now it's normalized asymmetric matrix Laplacian matrix, like defined by this way. But we know that because these two are symmetric, means similar matrix. That means the eigenvalue of this matrix are same as the eigenvalue of this matrix, but the eigenvector are different. So following we are consider clustering as a graph card. So always graph cut means just cut graph into two parts, but here we are considered for k ways cut, means cut graph into k partitions. And here is some definition for weight between two vertex set. Means one vertex from S, one vertex from T, and the edges, the weight of those edges where or takes a summation, then this means the weights between two set. And S bar means a complementary set of the vertex. That means S bar equal to totally vertex minus S. And the volume of the cluster Ci means all the weight of the edge inside S, inside Ci, means denoted by this way. And here also some definition. Means this vector, if I equal to 1, that means Vi belong to Ci, otherwise 0. So easily we have this kind of relations. And so here is two kind of card. One is ratio card and another is normalized card. Ratio card is defined by this way. And our aim is to minimize this value, means this value. Then we can get our final, means if we minimize this value, then we can get a better clustering. And here you see this value actually, by some method, we can conclude that always this value, minimum of this value equal to lambda m plus, means k smallest eigenvalues of Laplacian matrix. That's the main idea about the clustering and related to the eigenvalues. And also similarly, for normalized card also we want to get the minimized value of this one. And so similarly, this value, minimum of this value equal to k smallest eigenvalue of normalized Laplacian matrix. And so the corresponding eigenvectors is we have to take care of that. Now I want to introduce the main process of the.
So how those concepts, those methods is related with the length reduction that we covered?
Right.
How that concept is related to the length reduction that we have covered?
Because already I said this is like graph cut. So graph cut is to minimize this value. But actually this value is related to the eigenvalues. So only since we have to find the k smallest eigenvalues, and finding the eigenvalues and then corresponding eigenvectors, we just consider the we have a new date of the all eigenvectors, all eigenvectors corresponding k smallest eigenvalues. So for this new data, we just using some like k-means clustering to cluster them. Then again, for original data, we can easily find the clustering. Yeah. So here is the main process I want to see. Means first, we want to for optimized solutions for this one and this one. So already we know this relate to the eigenvalues. So first since is for given date, we have to find the similarity matrix A. Then depends on the objective function, we can choose normalized Laplacian or Laplacian matrix. Then we find out the k smallest eigenvalues and eigenvectors of B. Then we have to put the eigenvalues in one new matrix like UN. UN means eigenvector corresponding to lambda n, the smallest, like this way. Then a new matrix will comes, and we have to normalize it for each rows. Then we get new matrix Y. Now we can now this means each rows means a point related to original date. So there's n rows, so there's n datas. Now we just use the k-means algorithm to divide the new point into k clusters. Then this process is finished. Yeah, I just summarize here. So now let's see the simulation with R, but which I did in the Sage. So we can see here. So first, we should install this package, but yeah, and so here we show the date, plot the date, but in C there's some problem. If you just put one plot, then the graph doesn't come. That's why I put two times. Yeah, it comes well. Then we find the similarity matrix. Here, because data is there's 100 data, so it will be 100 by 100. So, but here I just show you from first to 8. First means sub-matrix, 8 by 8 sub-matrix, like this way. Here you can see symmetric. This is 1, 1. This is 1, 2. This is 2, 1. So symmetric. This means point related, means itself means first point and first point. So they are 1 point. So their similarity means 1, means very close, means in the same position. Yeah. This means they are a little bit close, but this means they are very far from. Yeah. Here actually we are doing the weight with the distance. Yeah. Here, because for this matrix, if CS very far, so we don't need to consider those distance, like those weight we don't need to consider. Just we can put, example, 0. It's okay. Yeah, for this one, 0.0 something that we all can do like 0. So the matrix will be more simple. So this is means revised similarity matrix like this way, and then we add all the rows. Here we get degree, means 1 point, this one, 1 plus this one plus this one. We got the degree matrix. All the entries, or as the diagonal entries are degree and others are 0. We get D degree matrix. And D minus A. This is Laplacian matrix. Yeah. So this is normalized Laplacian matrix. Actually, I choose because already we know this matrix and this matrix have the same eigenvalues, but this looks more simple because here like 1 by root something, it will be more complicated. So I choose this matrix. So here you can say diagonal. Yeah, this one. This means inverse. So we got the normalized Laplacian like this way. Here we get eigenvalue of Laplacian matrix. This eigenvalue. So actually here is a list of the eigenvalue of the Laplacian matrix. So one eigenvalue lie here and others lie in this part. That's why we gave the k equal to 2, because 1 plus 1, because one eigenvalue is 0. So that's why we give 2. And also for normalized Laplacian eigenvalue, we find the eigenvalue graphs like this way. And here also line 1, and the others are very big difference with this one. So that's why we give k equal to 2. That's a way to decide its k, how many clusters we have to do. So here we put all the eigenvectors in one set and doing the k-means clustering. Then we get, by the eigenvectors, we cluster for original date like this way. And similarly, for the normalized Laplacian, also we did by, and the same result comes. But what we want to compare with other method like k-means method, k-means clustering method. So for here's for given data, and we give the k means separate 2 part, means here 2. Then we got this graph. So actually it's not suitable clustering. And if we give the 3, also like this way, yeah, also it's not suitable clustering. But for Laplacian case, also this is one graph, but some random, because the data is randomly created. So sometimes you can say Laplacian matrix doesn't work very well because 2 eigenvalues are very small. That means 3 eigenvalues. We have to take k equal to 3. In that case, actually, it's from original data, we can see that always we have to consider clustering k should be 2. But here, for some cases, it not make sense that k should be 3. Oh, k should be 2. Because for this case, k should be 3. But actually, it's not like that. But for that case, if we consider normalized Laplacian matrix, always just one eigenvalue is separate with others. That means another one is 0. So totally is 2. So again, the 2 should be the final choice. For this case, this matrix make more sense than others. Yeah. And here's conclusions. Oh. And the success of the spectral clustering is mainly based on the fact it doesn't make any exceptions on form of the cluster. Means opposed to the k-means, where the result clustering are always convex set. Means if the data are convex set, that time k-means can works well. But others case it can be not works well. But for spectral clustering can solve this kind for general problems. And also, spectral clustering can deal with a large data set, because if we just divide to 2 parts, so for normalized Laplacian case, we only have to deal with one, means the second smallest eigenvalues. So it's quite easy, and the calculation is not very big. And also, for spectral clustering, we only have to solve the linear problems, just eigenvalue problems. And also, there's many algorithms to finding out the eigenvalues quickly. So But already mentioned that we choosing a good similarity graph is not trivial. We have to find the suitable similarity graphs, then makes our output looks more better. Yeah. And here's some references. And here's one more example with Python. Actually, here's original data. So, as we know, 1, 2, 3, maybe 3 clustering, right? Here's eigenvalues. But here, maybe not. So, actually here, not very big difference. Means not very big difference. But from here, but we know that's 3. So, for original data, we can say that we have to take 3 clustering. So we choose the first 3 eigenvalues. That means first 3 eigenvectors. Here, here the second smallest eigenvector, here third smallest eigenvector. Because so this one should be one set, and this one should be one set. This one should be one set. That's why we can take 3 clustering, and also from here also we can easily. Means this direction is second smallest eigenvector. This direction is third smallest eigenvector. So we only have to do in these data. So finally we get 3 clustering. So we have to divide 3, and this response means corresponding oriented data are here, and here, 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 like this way. Then we get the final one. But yeah. So finally, also we show one more example about the spectral clustering with Python, and here they are dealing with the Laplacian Matrix. And here one disadvantage is that we cannot easily guarantee that how to choose the value k. Yeah. And in the future work, I have to use this one to compare with using the normalized Laplacian matrix and compare the results, and maybe in that case our conclusion will be more clear. Yeah. And this is all for this presentation, and thank you for everyone. Yeah.
Okay. Later.
In this project, some kind of matrices introduced. First one is called weighted adjacency matrix. This is how to relate it at vertices. This is also symmetric matrices, and next one is normalized adjacency matrix. This is like this, and Laplacian matrix. This one well known matrices, and normalized symmetric Laplacian matrix like this, and last one is normalized asymmetric matrix, symmetric Laplacian matrix. This formula, and there is some all matrices, some. First one is eigen value has one one is eigenvalue of M. Corresponding eigenvalue is this, and Laplacian matrix is all eigenvalues positive and smallest one is 0.
Since Kappa is a new student on this area, second semester in the
clustering as graph cuts is supposed to denote see all clustering indicator vector. This is this formula. If VE belong to C, then C is
okay. So yeah, you went through those. So what you like to say finally after you done this project? But is there anything that you like to say to others after you did finish your project?
Spectral clustering is post similarity matrix. We have to find similarity matrix A. Then we compute maybe a normalized adjacency matrix or
So just say just one thing. What you have learned most from this project? What's the most important thing that you have learned from this project?
And we have compute smallest eigen values and eigenvectors, and then we another data set using there is we have to Cummings algorithm use. Then compute first compute corresponding matrix this. There is algorithm find eigenvalues, and
so if you do not understand that, then just ask again and understand the question, and then try to answer on that question, not just to say something else. Just so close it. Yeah, you take it.
So since those kind of explanation for the figures is necessary, so I will be upload more informations about this part in the iCampus, and then it's more better for others to understand. Yeah, I think so. And so.
What is the final comment after your project done? What you have felt, and what's the next thing that you may try?
Yeah, actually, first when I get this kind of topic, I don't have any idea. But after go through how it relates to eigenvalues, then I feel it's very the importance of the matrix and especially eigenvalues. And so for the future, maybe I have to go more deep about the eigenvalue, how eigenvalues can give some property of the original data, and it will be quite useful for us. Yeah.
Okay. I think we found what they have done, and there were just some suggestions to finalize this project. And as I mentioned, you should have the big picture of your project, and you should have a final comment, and which indicate the role of each participant and the after work note on it. I think that's the end of the presentation today. And any questions or comment?